I've mentioned linear systems previously, but I haven't given a real definition of what a linear system is. Linearity is defined in terms of a property called superposition, which is the subject of this video. Superposition governs the behavior of a linear system with multiple inputs. Suppose I have a linear system as shown here. If I apply an input x1 of t to the system, the corresponding output is y1 of t. If I apply a different input, x2 of t, to the same system, the output is y2 of t. If this system is linear, I can define the response of the system to combinations of these inputs in terms of combinations of these outputs. Specifically, if I multiply the first input, x1, by some number alpha, and the second input, x2, by a number beta, and then add those two signals together and apply that input to the system, the output will be alpha times y1 of t plus beta times the second output, y2 of t. An example of a linear system is this dependent source. The source output voltage is some gain K times V1, which is the voltage over here. That makes this a voltage-controlled voltage source. For my specific example here, I'm going to use a dependent source gain of 2. If the voltage V1 now is equal to 3 volts, the output voltage is 3 times 2, or 6 volts. If the input voltage V1 is 2 volts, the output voltage is 4 volts. Now let's take a look at what the output is if V1 is equal to the sum of the previous two inputs. So if V1 is 5 volts, 2 plus 3, then the output is 2 times 5 volts, or 10 volts. This is the same as the sum of the two previous outputs. Since the system is linear, the output resulting from the sum of the two inputs is the same as the sum of the outputs due to the individual inputs. Superposition is used a lot in the analysis of engineering systems, but I'll focus on one particular use at the moment, which is analysis of circuits with multiple sources. Power supplies can be considered to be inputs to our circuits. If we have multiple power sources in a circuit, this property means that we can calculate the circuit response to each power source individually and then add up the individual outputs to get the response to all the power sources. The approach is as follows. In order to find the response of the circuit to an individual power source, kill all of the other sources except for the one of interest, and then calculate the output value due to that source that you didn't kill. Repeat this process for each source in the circuit. Finally, after calculating the response to each individual source, add up all of those values to get the total response to all the sources. Now I'll do an example to illustrate this process. Our example circuit has two sources, a 1 amp current source and a 2 volt voltage source. I'll use superposition to find this current through the 4 ohm resistor. First, I'll look at the 2 volt source. To look at the contribution from the 2 volt source, I kill the 1 amp source, leaving the 2 volt source in place. So 2 volts, 2 ohms, this 4 ohm resistor, and killing a current source results in an open circuit. The current through the 4 ohm resistor is only due to this 2 volt source. I'll call that I1. In this particular case, Ohm's law tells me that the equivalent resistance here is 6 ohms, so the current through this leg is 2 volts over 6 ohms, or I1 is equal to 1/3 of an amp. Next, I'll take a look at the response due to the 1 amp source. Killing the 2 volt source results in a short circuit. And I leave the 1 amp source in place. And this current I'm going to call I2, which I can now use a current divider formula on. So I2 is equal to the total current, 1 amp, times the other resistance, 2 ohms, over 2 ohms plus 4 ohms. That's also 1/3 of an amp. Now the total current, I, is equal to I1 plus I2. I superimpose the individual outputs, which is 1/3 of an amp plus 1/3 of an amp, or I is equal to 2/3 of an amp. Next, I'll use the concepts of superposition and linear systems to develop two very useful circuit analysis tools, Thevenin's theorem and Norton's theorem.